Right, so if you have any questions at any moment, just interrupt me, because I will be talking about a lot of type level stuff, and since I want to cover quite a bit of ground, and the main topic of the talk is not actually introducing the type level stuff, but explaining what I want to do with it, I need a little bit of your guidance during the talk, like when I should explain more and when I should explain less. So I trust you to interrupt me accordingly. So what I want to talk about is the problem of, essentially, of migration, of data type migration. So when you write an application, regardless of what programming language it is in, your data types evolve over time, typically. You start out with a particular set of data types that cover your application domain, and then over time they change. So here is a contrived example. You have a user type which perhaps starts out with 3 elements, a login, a full name, and a location, and then you decide at some point, oh no, actually we don't need the location anymore, so you remove that. And then you decide at some point that actually I want to record for every user what their favorite programming languages are. And you add that as an extra field again. And then perhaps you say, well, actually I would like to more systematically record what the favorite programming languages of the user are. And then you say you change the languages from a string to a list of language or something like that. And you can imagine that you have many more steps like this. And so your data type evolves over time. And if you have a larger application and you have many more data types, then all of these data types change over time. So why is it a problem? I mean, in Haskell, first of all, it mostly isn't so much within the program itself. The type system pretty much has us covered. So if we change our data types, we can just embrace the refactoring skills that Haskell gives us. We call GHC. We look at the 150 type error messages. We jump to the according lines. We fix everything. And once we have made all the changes, the program just still works and passes all the tests. Or perhaps it doesn't, and then we fix the tests and add a couple of things. But basically, as long as the program or the application itself is considered, you don't really want to worry about old versions of data types. You just want to change them all, and you want to make all the changes at once. And the type system generally is relatively good in ensuring that you do that properly. But as soon as there are any external representations of your data, it becomes slightly more difficult. And there may be quite a few. So your programs communicate in some ways, or sometimes they just communicate with themselves. They create cached data on the disk, or they send messages to other processes, or they receive requests, or they store stuff in databases, and so on and so forth. And if the external representations are tied to your Haskell data types, then you may want to change the external representations as well, but you're not sure whether there aren't still any old versions in the wild, right? I mean, if you have a server-client architecture, you might still have clients that send requests according to the old format, because not all your users have upgraded at the same time that you have upgraded your server. Or if you have a database that is shared between multiple processes somehow, then you might still have some processes that write database entries according to the old format, or something like that. And all these things can happen. So you have to worry about what do you do with the versioning of the data. And so this is quite a large space, and there are quite a number of solutions already in the Haskell world, and I have experience with some of them. certainly not all. I may not even be aware of all. I want to mention a couple of examples that are particularly interesting in the setting of binary encodings, because they both support that. Oh, actually, yeah, so I mean, here is an example for a JSON-like encoding for how it would look with the first version and the last version of the data types, and how the external representation might change. And you might want to have an application that can somehow deal with both of these versions or any of these versions in between. So yeah, so two options that are available for example, for dealing with version binary encodings are safe copy and API tools. Safe copy is a package that allows you to define essentially all different versions as separate Haskell data types. So you really define all these different versions of the data type. So rather than having one user data type, you'd have 4 or 5. And then you define migration functions between the versions manually. And then you instantiate the class. And the final step is relatively simple. But then you've done all the work already. You've basically given instances for binary encoding for each of the versions. You've given migration functions, and then safe copy gives you a version binary decoding function that can decode a version serialized value and automatically migrate it to the latest version within your application. So this is something that safe copy can do, and that's quite good. API tools is another alternative. It's something that we are using at Well-Tapped at one of our clients. It's a DSL that allows you to describe the changes between versions of data types, and that DSL is essentially interpreted within a template Haskell quasi-quotation kind of thing. And it looks rather nice, and then there is a lot of template Haskell magic going on to derive all sorts of version decoders, and you can actually not just do binary decoding and encoding, but other things in a versioned way with it as well. So API tools is rather nice, actually. The only thing I dislike about it personally is that it relies so overly much about template Haskell, and even though template Haskell is extremely useful from a more theoretical academic perspective, I'm always not so content with it, because it's so unclear what it actually does, and it's relatively difficult to give clear guarantees for when does it actually work, or when will it actually fail, and is it actually really truly type safe, or have you covered all cases, because all the meta programming happens kind of behind the scenes in a relatively untyped fashion. So I was interested because historically I'm working on data type generic programming all the time. So basically my PhD was on data type generic programming, and that has remained a hobby of mine for all the years. So I was interested in seeing whether I couldn't apply data type generic programming to this problem and do something like API tools, but without template Haskell, and instead by using data type generic programming. So before I go on, I should again say that this is just 2 libraries out of many. So for example, there is persistent, which is another big library that deals with migrations as well, in particular more targeted at databases. And so there are many more. If you have, I would still like to hear, like, if you have active experience with any of these at the end of the talk, perhaps we can discuss a little bit, because it's relatively difficult to find kind of all the features you might want to have for a system that is really good. So if you have anything to contribute, I would like to hear from you. Okay, so what is data type generic programming? I think I looked a little bit at the history of Monadic Warsaw, and I think Ollie Charles was here and gave a talk, and he has already talked to you about datatype-generic programming a bit, but I'll give you my summary. So the basic idea of datatype-generic programming is that you basically want to forget about the fact that Haskell has a nominal type system for a moment. So Haskell data types essentially do two things. They define something which is structurally always very similar, in the sense that you always define a data type to be a choice of one of several constructors, and every constructor is just a sequence of fields. So essentially, it's all just about choices and combining things, and that's what really makes data types. But then there is this additional thing that it also says you create a new name, and that data type of that new name is different from all other data types that exist so far, regardless of whether they have the same structure or not. Right? So even if you define your own data type that is exactly like lists, and that it has two constructors, and one represents the empty list and the other takes an element and a tail list and forms a new list, it'll still be different, right? And new types take that to the extreme, where you say you take an existing type and just give it a new name and treat it as different. But sometimes you would like to define algorithms that are just over the structure of the data types. They may still involve the names in one way or the other, but they are primarily about the structure. And, a very typical example would be just structural equality of data types, something that you can usually derive. But what's the algorithm for structural equality of two values of an arbitrary data type? You check whether the two values are of the same constructor, and if they are, you check for all the fields point-wise whether they're also equal, right, recursively. But that's an algorithm you can describe by referring to things like the same constructor or all the fields without any knowledge of what concrete data type you started with. And that is exactly what the deriving construct in GHC implements for equality. So binary serialization is another classical example. If you can develop multiple different ways of serializing values efficiently, and you can be more clever or less clever. But in most cases, you're just interested in having a compact binary representation that you can read back again, that is determined by the structure of the data type, and you can uniformly derive such a serialization and deserialization function for any data type. So yes.
Data type, that's different than just type, because you're saying type sometimes.
Yeah, I'm slightly fuzzy in the terminology, but yeah, when I emphasize data type, then I usually mean a type that is defined by using the data construct in Haskell, but there's no real distinction between the two things. So, yeah. Sorry. Yeah. I hope this will become clear. So I mean, in general, so the idea of data type generic programming is that we are forgetting about the names. We're giving data types a uniform structural representation, and that structural representation is different from the original data type because it collapses things that may have different names into the same structure. But we can convert between the original data type and its structural representation back and forth. And then we can define functions based on the structural representation that thereby work on many different data types. That is the core idea of data type generic programming. And it needs some kind of help from the compiler because you need to get some, either you have to bring in template Haskell again, or you need help from the compiler in some other way, because you need to get such a structural representation. You cannot just magically conjure that up. Or you have to manually define it for every data type, but then it's not fun at all. So, so you want to have some help. And over the years, there are many different flavors of data type generic programming that have been developed and promoted. And this is really nowhere near an exhaustive list, but probably the two most well-known approaches these days are GHC generics, which is a built-in form into GHC, and scrap your boilerplate, which is also built into GHC. So these are the two approaches that are both supported by GHC directly in one way or the other. And then most of the others rely on a little bit of template Haskell. So Uniplate is a simpler form of scrap your boilerplate. Generics SOP is the one that I'm actually going to talk about for the rest of this talk. Multirec is, and comp data as well, they're more fancy approaches that are helping with, if you actually want to derive recursion schemes over systems of mutually recursive data types in some complicated way. So, and then there are more. There are like replib, and then there's cure, and there's, there are probably at least 30 libraries, if not more, on Hackage that are in one way or the other data type generic programming related. So mostly you can do the same things with them, and they have slightly different flavors. So I want to talk about generics SOP, and simply because this is a library that I have been co-developing with a colleague of mine, Etzko de Vries, within the last few years. And we've used it in quite a number of applications successfully, and I think it is nice because it encourages a style of programming that is very reusable and is based on higher order functions and combinators, and has a very functional flavor. So most of the generic functions you're defining using generics SOP are actually compositions of smaller functions that are already given by the library. So that is a nice aspect. The perhaps not so nice aspect of it is that generics SOP relies on almost every type system extension that GHC has to offer, which makes it not so easy to explain and not so easy to access and get started with, in particular if you're not that familiar with these parts of Haskell. So I'll give a high-level introduction to it a little bit. So the basic idea here is that if you have a data type like this one, the user type, in one version of the versions that we have seen so far, then the first thing that generics SOP does is it associates every data type with a so-called code. And the code is a type-level list of lists. And that's this thing here. Right. And you can think of it as I said, I mean, the essence of data type generic programming is focusing on the structure and forgetting about the names for the time being. And if you think about what is the structure of a data type, as I said, a data type essentially is a choice between different constructors, and you can think of every constructor is in one line, and then every constructor has a number of fields, and the fields you write in one line. So if you drop all the names, you essentially have a matrix, a two-dimensional matrix of types. And that's what the code is. So the code is a list of lists the outer list contains one element per constructor, and the inner lists contain the types of the fields of each constructor. So in the case of user, the outer list contains a single element because we have a record type and it just has a single constructor, which is also called user here. And the one inner list contains 3 elements, and these elements are the type text, and again the type text, and the type list of language. Right. And unfortunately, syntactically, Haskell becomes quite ugly on the type level because there is a lot of clashes and ambiguity going on due to the way that the Haskell syntax has been designed back in the day when nobody was thinking about type-level programming. And so you can see one of the problems right here. This is a list, this is the type list of language, right? But since we now have type-level lists, you have to disambiguate from a type-level list that contains one element, which is the type language, on one hand, and the type of lists of languages on the other hand. And so if you don't write the strange tick in front of the bracket, then it will be interpreted classically as the type of lists of languages. But if you do, then it will actually be interpreted as a type level list. Okay? So let me live show another example.
So do you have to write this representation yourself, or is it generated automatically?
Okay, so this one is generated for you by generics SOP. So you can, if you want to play with different representations yourself or things like that. So there's nothing being generated that you couldn't write yourself, but no, but you don't actually have to write it. So yeah, let me give an example. So can you read this?
Yeah.
All right. So so you can, with :kind bang, you can actually evaluate type families or type level functions in GHCI, in case you don't know. So you can, for example, ask for the code of either int, or bool, something like that. And if we remember how either is defined, well, that wasn't helpful. If you remember how either is defined, either is a data type that has 2 constructors, left A or right B, right? And every constructor has a single field. Therefore, the code is a outer list which has 2 elements, one for each constructor. And now the first inner list has an argument of type int. That's because we instantiated either to int and bool, and the second one has a single element, which is a bool, right? And let me see if I can actually do this all within GHCI. If I define, or perhaps I can just load the user one.
So it is losing some information because it doesn't contain the labels, the left and right, the constructor names.
Right. So at first that seems like an advantage. We'll later see that it is not entirely an advantage. But for things like equality, right, you don't need the labels, right? And you basically want to like if you want to derive an equality function for a data type, you want to write something like I just want to know whether they are of the same constructor, and I just want to combine the fields. And you would still like to have the type safety in the sense that you know that originally both values have been from the same data type. And if you go through 2 values and are of the same constructor simultaneously, that the two values that you end up comparing with each other will each be of the same data type again. So that kind of structure you want to retain, but whether there were any record field labels or what the constructor names were or what the data type name was is not important for this kind of thing. There are other functions that are also data type generic where it does matter. For example, the show function, like if you want to have a human readable textual representation of a data type, that is something that you can also describe algorithmically without referring to a concrete data type, but when you describe it, you will say, at this point, I want to insert the name of the current constructor or whatever it is. So the names still play a role, but not a role for distinguishing the different types very much from each other.
So that's the approach that generic SOP takes? It ignores the names?
You can still get at them. So actually, but we'll get back to that in this talk anyway in a slightly different way. But also in generic SOP, you can query the name of the current constructor if you need to. But first and foremost, you just focus on the structure of a data type and drop them. Right, so and I can also look at the code of this user data type that is listed up there again, and then in this case I have login full name and location, all three of which are string, and I just have a single constructor, so I get 3 strings again.
I think there was a question.
Oh, sorry.
Sorry, did they install, but what if you have 2 constructors of the same type that take the same time? For example, that one constructor that takes a string and another constructor that takes a string. But constructs different based on that.
So the position in this matrix still matters, right? So and the order of things. So this is very much in line with what Haskell already does. If you like a more radical example even of what you're saying is if you just have an enumeration type, then you have many constructors, each of which don't take any argument whatsoever. So if I just add one here, or no, I can just do ordering. Ordering is a good example. Ordering is an enumeration type with 3 constructors, LT, EQ, and GT, each of which have no argument. And if I ask for the code of ordering, I get this list. I can bring that up a bit. And so again, you get an outer list which has 3 elements because you have 3 constructors, and the inner lists just have are just all empty. But that doesn't mean that you cannot still distinguish the first from the second constructor and the second from the third. And for example, if you would derive or if you would define something like a generic comparison function that compares values of data types, the way that Haskell's deriving ORD works is also that it always considers the first constructor to be smaller than the second constructor. So the order in which you define the constructors of a data type is observable and matters. But if they are type compatible, then of course you could define a function that flips them or something like that. So you're free to do things that work. Okay, so the code is really just the first step. Sorry. The next thing then is that the actual representation of the user type is defined to be a sum of products. That's what SOP stands for. of the code of users. And I won't have time to go into this in great detail, but I can show how that looks like by taking an example user. I have an example user in here, Andres, and converting that one to the generic representation using from. And so this contains the same information again as the original data type, but in a sort of uniform structural way. So it starts with, I can bring that up again, it starts with SOP, which is just a dummy constructor that stands for sum of products. Then there is a Z, which actually you can read as 0, which represents the first constructor, but it basically only numbers the constructor. So it says this is belonging to the first constructor. And then it contains a sequence of fields, and that's a heterogeneous list, if you like. I mean, in this case, it actually contains 3 strings, but if the data type would contain fields of different types, it could theoretically contain different things. But it is essentially like a list, right? The colon star constructor is very much like a cons, and the nil is very much like an empty list. But it contains these different things. So, and if you have this generic representation, you can convert a data type into this SOP form, and then you have all sorts of functions provided by the library that operate on these sums of products. So you can map over these heterogeneous lists if you have a sufficiently polymorphic function. And so on and so forth, and that way you can define generic functions. So so actually we can play with this a little bit. I can, just to make it slightly more interesting for the moment, I can add a I don't know, identifier that is an integer, so that we have one different type, and then all the rest won't work anymore because I have other definitions down here, which I will comment out for the time being. So let's work with these. Do I still have because I commented Andres out, which of course I also have to adapt. So, okay, yeah. So a typical thing that goes into the direction of serialization is, for example, if I know that all the elements in my data type, all the components in my data type are in the class show, then I can apply show to each of these elements, even though it's a heterogeneous list. And so this would work by invoking a magic function that's called hcmap, which is for heterogeneous constrained map. Constrained because we are working within a type class, which is show. And then the type checker in GHC actually needs help, and we have to tell the type checker explicitly how which class we mean, and we do that using a proxy. So that is a thing which we only pass in order to fix which type class we're using. And then we have to say what we actually want to do with each of these elements. And in principle, we would like to just say show, but you can see these i's in front of each of the strings and the number in the end. And the I is actually short for identity. So every element in the heterogeneous list is parameterized by a type constructor, which is in the normal case the identity type constructor, but we can pick a different one. And in fact, so the code, if you remember, the code says string, 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 int in this case now. But if we apply show to it, we'll get string, 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 string. So we'll get string everywhere. But the code remains the same. So the code of the original heterogeneous list and of the target heterogeneous list is the same. So it's nice that we can switch from the identity functor to the constant string functor while applying the show function, so that we can essentially turn the heterogeneous list into a homogeneous list.
But that will be inside the SOP representation, right? We can't actually magically move it into our type, create a new one.
No, this is all on the representation level, right? So we have applied from, but we have not applied to. So afterwards we could not apply to anymore. So okay, so I should perhaps do this before. So I can actually go back to the original type, but I have to say what it is. So, right, I mean the conversion works both ways, right?
And the dumb question, what if you give a wrong type? Will it be a runtime error? Or?
No, it will be a compile time error if it's a type that has a different code. And if it's a type that has the same code, it will actually work. So you can write a very straightforward structural coercion function using generics SOP by just saying to after from. That says like you can convert any two types into each other that are both an instance of the generic class that SOP defines and that have the same code. But this is enforced on the type level. It's not a runtime error. It's a type error. Okay, so let's go back to hcmap proxy show, and then yeah. So the way I have to unwrap the element from the I functor and then apply show to it and then embed it into the constant functor. And that I can apply to it. And then I get a representation that looks just like the previous one in structure, but now every element is a string, and every element has had show applied to it, which means all the strings get extra quotes, as show does, and the integer becomes a string integer. And then once you have something like this, you notice you actually have a homogeneous list because you're using the constant functor everywhere. So then there is another function that's called hcollapse that can turn this into a normal Haskell list again. And then you can do something like concatenate it or put spaces in between or put commas in between or generate some kind of actual textual representation from it, right? And so other serialization functions work in a similar way. The binary encoding it works essentially also by mapping recursively the binary encoding over all the argument values of a constructor, and then just encoding the constructor somehow. And well, one very naive but plausible way of encoding the constructor is just say, you determine what is the number of the constructor, how many constructors are there in total, and then you determine how many bits you need to uniquely encode the constructor, and then you do that. And that is a naive possible binary encoding. Okay. When did I actually start so that I know when my hour is?
Depends how much time you want to spend. If you want to go for another half an hour.
I want to spend roughly an hour.
Well, then you have 10 more minutes. But if you want to.
But we didn't start at 8, right?
Oh, yeah, right. But you
did we? Or at 7, or did we? Well, I mean, okay. You have to tell me when to stop. But 10 more minutes at least. Okay, so that's good. Right. I think I basically explained most of this. So now you can imagine that you can use this machinery to define generic functions like a generic encoder and a generic decoder. And this is just one example of how this could look. And this is more for demonstration purposes than for actually being efficient, because you would not actually use a Haskell list of a type bit, but you would actually use some kind of byte string or whatever as a result if you wanted to have a truly binary encoding. But algorithmically, it's essentially this what you want to do, right? You want to turn a value of some type A into a list of bits. And then the decoder is slightly more complicated, which is why I've left it an abstract type. So if you've ever looked at parser combinators in Haskell, you want to do something like either maintain a cursor into the input list of bits, or have each decoder return the rest, the unconsumed rest of the bits that it hasn't encoded. And then you can, using the generics SOP machinery, define a generic encoder and generic decoder that has the following types. So this is a typical type signature that generic functions in generics SOP will have. So the actual types are like the types of the class above, but then there are extra constraints that say you can define encode generically for everything that is representable, for which you've derived the structural representation, which, as I said, works essentially via a little bit of template Haskell. And in addition, you need to know that all the component types of the type are also in the encode class. And that's what this all2 thing does. All2 is another type level function, if you like to think that way, that computes a constraint over a type level list of types. So code of A is a matrix of types, and all2, you can just imagine, says that every element that occurs in this matrix has to be in this class. All right. So if I have, sorry, what was the kind of code user? If I have string and string and string and int in here, then actually I can even do that. I can ask what is all2 of encode of code user. Doesn't expand it. That is because that's because I defined it more cleverly. Okay, so if I take another 5 minutes, I can actually define my own version of all2 as a type family myself, so that you can see that. All2 of, so if you have a constraint, and well, let's actually just do the one layer, and the type level list, a list of types, then you get a constraint out. And then the straightforward way is just to say, this is essentially just mapping the constraint over the type level list. So this is C of X followed by all C XS, all prime, I should say. So if you haven't seen this before, the type family is all on the type level, but it looks more or less like a function definition, so it also has multiple cases. The first argument of all prime is actually something that, so this doesn't need to be a type. This is polymorphic. So the first thing is something that takes something to a constraint, and the second thing is a type level list of whatever, and then the result is a single constraint. And if we compute all over the empty list, then we get the empty constraint, which is also written like the unit type, so there's another kind of syntactic overlap, which is disambiguated ad hoc by GHC just because it knows that the result kind is constraint in this case. And the second line says if we compute all over a non-empty type level list, then we have the constraint C of x followed by the recursive invocation of all for the tail of the list. So let's see if this compiles. No, because I need to enable more language extensions in here. Polykinds and constraint kinds and type operators and then I need to import GHCX for the actual name constraint. Okay, and then I can demonstrate what happens if I call all prime of encode on, say, string int, like it happens in our. Now I need to enable the language extensions in GHCI as well. Okay, but now you can see that it actually expands it. This expands into the list of constraints, and of course if there is multiple times the same constraint, it will just be resolved by GHC's constraint solver nicely. But so this is a way that all2 is defined similarly over two-dimensional lists, or like matrices as they occur in the actual code. But it basically just maps a constraint over all the types that are contained. Okay, so this is a way to get unversioned generic encoding and decoding. But now we would like to have versioned generic encoding and decoding, and we have seen that we have morally in our example, 4 different versions of the user type. It doesn't really matter anymore what they were, but they were 4 different versions, and the 4th one is the one that we currently want to work with. But if you think about it, all 4 have different codes, right? So if you compute the codes of them, then they will typically be different. There are situations thinkable where the code would not actually change, because you might just rename a constructor or rename a field. I'll come to that in a moment, but for all the ones that I've actually shown before, the code will actually change. And now you can imagine that you have a type migration that explains how to go from a representation of one type to a representation of another, and that essentially gives you a conversion function that operates on the structural representations, not on the original data types, but on the structural representations. And now the nice thing is that because all your migrations, if you use this data type, work on the structural representations, you actually, in principle, if you have all these migration functions somehow, you don't need the old versions of the data type at all anymore, because you can just work with the structural representations. If we can, morally speaking, if we know somehow what the codes of the old versions are, and we can generically define encoders and decoders for everything that has a code, and we have the migration functions that also operate on the structural representations, then it's enough to know the current version of the data type and these migrations to somehow do all the magic, to derive a versioned encoder or decoder that somehow attaches a version identifier to the serialized value, and then when it deserializes the value, it detects which version it was and applies the right number of migration functions. Okay. Is that a question? Or just a thought? Okay. And now you want to chain these migrations, and one way to do that is to use a history data type, which is like this. I've omitted a little bit of detail there, where you say you have an initial revision, and then you have new revisions, and essentially every revision attaches a version, which is an arbitrary identifier. I'm going to use type level strings in a moment. And then it's again a list-like structure. So if you look at it, initial is like an empty list, and revision is like adding a single migration to an already existing history. So essentially a history is a list of migrations, but the type indices are indicating that they are chaining the codes properly. So the initial revision starts with a particular code C, but then if you add a new revision, then the migration that you add has to go from some code C prime to C, and the history has to be for C prime, the remaining history. So these are compatible.
Question.
Yeah.
Just to make sure I didn't get lost. So we do it because we at some point have functions that run on our latest version and want to accept data that was a previous version, right? Mm-hmm. So what happens if, when going through the versions, you say delete a list of languages, then some versions later you add it back? That data would have to be empty then, right? Because you apply those step by step.
Yes. So if you like with this approach, if you remove data and later add it back, there is hardly any way that you can retain it unless you just moved it around in your data type. I mean, that can happen if you say something like, I'm removing this field, but the information doesn't get lost, it rather gets stored somewhere else, and then later you move it back, then you may also be able to recover it. But yeah, if you drop it completely, then it would fail. I mean, as I said, there are many variables in this, and one particular assumption here is that you have something like a linear history where you do everything step by step. There are also options of essentially doing things like shortcutting across many versions at once, or having better migration functions that go larger steps directly. I mean, there are all sorts of modifications thinkable, which I believe are all expressible. The question is, in a way, what is the sweet spot in the design, which is why this is all ongoing work and not finished. And I haven't made all the decisions yet. And I'm very happy to take more input on what you think should be more important and what should be less important. But yeah, you're right. So once you have this, you can define a simple migration very easily, like adding a new constructor to the beginning of the list, basically in front, that doesn't have any arguments, can be defined like this: migration shift, where shift is actually an easy to define function that just moves everything up, right? One layer. But but this kind of style is not very nice, because you're talking about your migrations now by position rather than name, and And so that's not really what you want. You want to write down something like, I added the constructor that has this and this name, or I added a field that has this and that name, or I deleted this and that constructor. You don't want to write down, I deleted the third constructor of a data type with 20 constructors, because you'll never remember what the third constructor was at that time. And if ever anything goes wrong, the error messages will be horrible. So you need, here you need access to the names. And actually ultimately we need access to the names on the type level as well, because everything should be statically checked. I mean, if I write down a migration that says I want to remove the constructor with this name, I want it to be a type error, a compile time error, if the constructor doesn't actually exist, rather than a runtime error. So it should be information that is available at the type level. So this is where we sort of extend the current state of generics SOP. There is actually a branch in generics SOP that has this already for some time, but again, there are many different ways in which you can do it, and I'm not completely sure yet what ultimately the best way to do it is. But we want to include names in code sometimes. So, so this was the original way that codes work. And here are codes with metadata. So this is a very simple way of extending codes with metadata. Rather than saying the code is just a list of types, we are adding a type level string, which in GHC is called symbol, at every layer, both at the inner layer and at the outer layer. And then, for example, the code for user gets on the outer layer an additional label user, which is the name of the constructor. And at the inner layer, it gets labels login and full name, which are the names of the fields. And then it's very straightforward, again, by just iterating over the list to drop these names again if you don't need them, right? So to define a type level function simplify that takes a metadata enriched code and removes all the metadata and just keeps the matrix. So you can say that your generic programming library can actually derive something like a meta code for your data type, but then you also still have the code. And if you have a function that doesn't need any of the metadata, you can just work with the plain code. And if you have a situation like in the migration setting where you do want to work with the metadata, you can use it. Right? So the way that the original generics SOP gives you access to metadata is different, is on the value level. But as I just said, for this migration setting is one of the examples where you want, where I think you want the information available on the type level. So this is a possible extension to generics SOP. So at the moment, the library won't derive the meta code for you automatically. At the moment, you have to write this one by hand, which kind of defeats the purpose, but it would be easy to change the library to give you the meta code instead. And then you can refine migrations to work on meta codes rather than on original codes. And the migration functions themselves, they would still work on the actual structural representation, which is based on the simplified code, but the code would be tagged with the two meta codes, which would involve all the labels that are involved, and then here is how you could define a concrete migration, and so a concrete migration that adds a field could say, for the version that's called V, at the constructor that's called D, I don't know why I called it D, but yeah, because I use C for something else. But and I want to add the field called F, and all these are type level things, so I pass in proxies to make that explicit. And then I give a default value for the field, which is used to derive the migration function automatically, right? The whole point is that I then don't have to write the manual migration function. I really can just say, I want to add this, this field to this constructor with this default value. And the migration function that basically says, I'll take an old value of the old structural representation and turn it into the new one, that if it is of any other constructor, it will be completely unchanged, and if it is of this constructor, it will gain this extra thing which has this value in it. That can be derived automatically. And that can then be used to add a migration function to an existing history. And similarly, you can define other migration. So the example that I showed in the beginning is can be written like this. So we had 4 revisions of the user data type, and code prime is actually I didn't actually show that, or did I? Oh no, it is. Code prime is the type family that derives the meta code. So it's the history for the meta code of user, and so it's backwards because it's function application. But I mean, we could define combinators to write it the other way around. I don't know what's better. But at the bottom is the initial revision, which was version 1, and then we removed the field location, and then we add the string field languages, which I'll give a default value of the string Haskell, and then I change the type of the field languages from string to list of language, and change type is a migration or a helper function that takes an explicit conversion function then. So I have to pass in a function from string to list of language here, which is parse languages, which I have defined, that is very naive in my demo code, but just basically applies read and looks whether it matches any of the existing constructors. But you could imagine something more sophisticated. And you can, again, these are variables, but I mean, the way this is defined, you can see that, for example, I haven't said explicitly what type the field languages is that I add. That is actually inferred from the default value here, because I'm giving a string, the type has to be string, and I'm also not saying explicitly what the types are that I change in the change type. That is inferred from parse languages, which is a function that goes from one type to another. So, but that is a choice. I mean, I could also make these explicit because they might actually serve a good documentation purpose in such a statement. But this is a way that you could write down a history of a data type. And then you can give a class for everything that has a history attached to it. That basically just attaches, gives you the history for a particular data type, and the current revision, which is the current version. And then you can write not just a generic encoding function, but a history-based encoding function, which is what we actually wanted. So encoding is actually rather straightforward. It just chooses the latest version from the history, it drops all others, but it encodes the version and it encodes the data generically using the old generic encoder. And then you can also write a history-based decoder, which is more interesting because it decodes the version, then it chooses the right version from the history, then it decodes the data generically for that version using the generic decoder, and then it applies all the migration functions, right? And so Yeah, at this point I'm almost at the end, but I would like to show that it works. So let's see, now I have to uncomment and undo all my changes here. Yeah, that one has to go as well. So this is the original version of my user data type. And this is an example of a user in the original version. And test 1 encodes the value undress using the old encoder to a database, which is essentially just a file, and I can actually look at that file. So, and as I said, I'm just using a list of bits here, not an actual binary encoding, so that you can, rather than having a completely cryptic list of binary garbage, you get a almost as cryptic list of bits.
Make a package.
Right, so this is what you get. And now test 2 first checks that I can still, with the old original version, just like do the round trip, so that I can actually get back from the database the right version. And I've actually there is a trace statement somewhere in my code that lists the versions of everything that is being read. So this is not really part of the output, but this is just so that you can see what's going on, so that it actually read a value of version 1 of user. And now we can go to user current. Sorry. And this is having the list of languages in there. I only admit 3 languages for the time being, but you could add more. And I'm actually making the languages versioned as well. And the user history looks like the one that I had on the slides. And so the encode instance for user in the way is in the end very generic. So we just use the history-based encode and the history-based decoder. So we don't have to do anything for this. So this is the main point, that you don't have to do anything for this. I mean, you could imagine you want this to be even simpler and an empty instance, and this can be achieved with a little bit of more trickery as well. But already, so at least there's no hard thinking involved at this point. And then this is for the languages. But for the languages, there's only a single revision. And now there is a value undress for the new type. And now I have 3 tests. So the first is just a round trip for, the first and second is just a round trip for the new version, that still works. Oh, I didn't actually load the... So this gives me back that value, and it actually lists 4 versions, 1 4 and 3 1s. The 1s are from the language values, because there are 3 language values in there, each of which is at version 1. And now test 3 actually looks at database 1 and decodes the value from there, which was written by the other code. So that should read a user of version 1 and apply the migration to it. And there you can see that it introduced the Haskell default value and then parsed it into the list, so it applied the migrations properly. So yeah, so that's the main content. So there's just discussion to be had. So there is a lot of things that are not quite nice about this. apart from the flexibility. So one thing that is actually a bad idea, I'm convinced about this, and this was the first approach that I did, where I did versioning by data type. So I'm now convinced that the approach that also API tools takes, that you're versioning an entire API, which many people do anyway, is actually much better. So you're, rather than defining different versions for every single data type possibly, you're just saying your entire application has a particular API, and that API has versions, and whenever you increment the version, you can perform many changes to many data types at once. Because if you have interactions between different data types, it otherwise becomes unmanageable. If you have two different version data types and one occurs within the other, and you're saying you're going from version 2 to version 3 for this one data type, and you're adding a field of this other version data type, then how do you write your migration function? Whereas if you version the entire API at once, you basically know at which stage you are, you know what the current versions of everything are, and you know in which terms you have to write things. And then there is a lot of flexibility in terms of do you want linear histories or not? Do you want only forward migrations, or do you also want backwards migrations? So backwards migrations are very useful as well if you want to support old data formats, for example, right? I mean, in the serialization setting, perhaps not so much, but even there, I mean, if you have some kind of binary format, and you still want to write files for an old version that can be read with other software. So, and then you need to basically have a way to not just keep track of the forward conversion functions, but also of the backward conversion functions. And you can do that, but you have to make choices everywhere, and you have to expose a nice API so that everything remains manageable. Then you want, of course, not just binary serialization, but you want to have JSON and databases and whatever all within a common framework as well. But the nice thing is that in principle you can, right? Because the codes give you all the information you should need, and you're quite flexible in what you can do. It's just some advanced work that someone has to figure out and write down. And just in general, I think this computing with types or with codes and with structural representations is something which is made possible by data type generic programming, but it is not a very explored field yet. So there may be other applications that are have nothing to do with migrations that I haven't thought about yet, that are other interesting things that you can do with this general idea. So, so a very straightforward example that we have actually thought about, that is even in the original paper about generics SOP, is something that doesn't really compute with the codes, but computes based on the code. So if you want to define something like a generic validation function, you might want to parameterize the generic validation function with specific validators for each of the fields of a data type. And you, of course, want to make sure that you provide a validator for each element that you actually have. So you want to maintain the type correctness of all the validation functions. And that is something that you can nicely express with codes. But if you actually modify the codes in between, like we do with migration, then there may be more options. Yes, that's it. It was long enough. Questions?
Well, I have a question. So do you think it would be possible to, because you have this history, right, which you specify manually how to go from version to another, would it be possible to somehow automatically generate those steps, or at least a first best approximation? Because, you know, when you delete the field, it sounds like it should be possible to say, okay, I've deleted the field, so the probable migration function between those two types is this.
So it depends on, you need to keep something around. I mean, the approach I took here was to say, when I actually make the change to the data type in my source code, I will make it destructively, but document what I've done by editing the history at the same time. And the compiler will check for me that I do these two things in a compatible way, otherwise I will also get a type error immediately. But what you could also do is, if you keep the old version around and basically rename it to something, you could define a function that says, like, given two data types, try to find something like an edit sequence that goes from one to the other, right? I mean, that is similar to diffing. You could have some kind of diff algorithm on code. So you say you have a number of primitive migrations that you allow. You could imagine writing a type level generic diff algorithm that takes two data types and comes up with a sequence of migration steps to go from one to the other. And then you could use something like that to say, I don't want to invent the migration myself. I personally would think that that is less useful on practice, though, because most of the time you have a particular logic in mind, like you're adding, like you for example, you cannot really expect any such thing to derive a sensible default value for a new field or something like that, or a conversion function of any sort. So typically when you perform a change to a data type, you have more information in mind anyway, so it makes sense to actually give you a way to write that down in a more structured way than just a comment. That is actually programmatic and type-checked and everything.
I was more thinking of like a helper function, so that you give it the two types, and it would give you the probable look of the migration function, but you would fill in the holes yourself still. So you wouldn't have to, for the simple migrations, you would just copy over what the helper function outputted to the code.
Yeah, possibly. I mean, doable, certainly. Yeah. Other questions?
Does this support recursive types?
Does it support recursive types? So, yeah, so the single version or version per data type that I presented here doesn't work nicely with recursive types either. But the unfinished version that I'm working on that does versioning for many data types at once should also support recursive types.